Have you ever been chatting with a large language model, and it confidently spits out an answer that's just, well, wrong?
Yeah. Or clearly from like 3 years ago. It happens all the time.
Exactly. It's like talking to that brilliant friend who knows a ton, but somehow missed everything important that happened since their last software update, especially about your specific world.
Mm-hmm. That's a great analogy.
Well, today we're diving deep into the secret sauce that fixes exactly that. We're talking about Retrieval-Augmented Generation, or RAG.
RAG, yeah.
Think of it as giving your AI its own super smart research assistant, one that can instantly pull up the most accurate, up-to-date information relevant to your question from your specific data.
That's a really good way to put it.
So we'll unpack how RAG fundamentally changes the game for LLMs, explore powerful frameworks like LlamaIndex that make building these systems surprisingly accessible,
And they really do make it easier.
and introduce you to the unsung hero that makes it all possible: vector databases, specifically ChromaDB.
Ah, yes, ChromaDB, crucial piece.
By the end of this deep dive, you'll not only understand a RAG, but also how you can ground LLM responses in your unique real-time knowledge.
So to start, let's maybe peel back the layers on this foundational concept, RAG.
Okay.
At its core, it's a brilliant fusion, really, of information retrieval and generative AI. It allows large language models to tap into vast, external, and highly specific knowledge bases, like, say, your company's latest policy manual or a detailed research paper.
Things it wasn't trained on initially.
Exactly. Without ever needing to be retrained, which is huge.
Right.
This means an LLM can answer specialized queries with pinpoint accuracy and contextual relevance, moving way beyond its general training data.
So it's not just guessing based on patterns.
Precisely. Now, the RAG process really comes down to two main acts, you could say.
Okay.
First, you have the retriever. Think of it like a lightning-fast librarian. It digs through your knowledge base to find precisely the most relevant snippets of information for your query.
Just the relevant bits.
Just the relevant bits. And second, you have the generator. This part then takes those retrieved snippets and uses them to craft a natural, coherent, and importantly, factually grounded response.
Ah, okay. Retriever and generator.
Yeah. And it's surprisingly logical in practice. It unfolds in 4 key steps.
Let's hear them.
First, text embedding. This is where the magic of meaning sort of begins. Both your user's question and all the documents in your knowledge base are transformed into these high-dimensional numerical vectors.
Vectors, just lists of numbers. Right?
Exactly. Long lists of numbers. Think of it like giving every piece of text its own unique GPS coordinate in a vast semantic landscape. Words or phrases that mean similar things get coordinates that are very close together.
So meaning becomes location.
You got it. Then comes retrieval. When you ask a question, its GPS coordinate, its vector, is matched against all the document vectors in your database.
How's that matching work?
Well, we measure the distance between your query's vector and every document's vector. The closer the distance, the more similar the meaning.
Like a semantic ruler.
Precisely. And one of the best ways we measure this similarity is through cosine similarity. It essentially measures how aligned two vectors are in their direction, which is great for meaning. The retriever then pulls out the documents with the closest, most relevant GPS coordinates.
Okay, so it finds the best matches.
Right. Third, we have augmented query creation. The retrieved content isn't just, handed directly to the LLM.
Right.
Instead, it's intelligently combined with your original question. This creates a much richer, context-aware prompt for the LLM.
So the LLM gets the question plus the relevant facts.
Exactly. And that leads to the final step, model generation. The LLM receives this augmented query, your question, now supercharged with the highly relevant retrieved information.
Mm-hmm.
With this specific context right in front of it, the LLM can generate an informed, accurate, and highly relevant response. It ensures it's grounded in current factual information rather than just what it learned during its last major training cycle.
Which avoids those wrong or stale answers we talked about?
That's the goal.
So, okay, if that's the core RAG recipe, the question quickly becomes, how do you actually cook this meal? Because building these RAG applications involves quite a few moving parts, right?
It definitely can, yeah.
And that right there is where frameworks like LlamaIndex become indispensable. LlamaIndex is purpose-built for what it calls LLM-powered context augmentation.
A bit of a mouthful, but accurate.
Yeah, essentially making your private, external, or proprietary data seamlessly accessible to an LLM so it can truly ground its responses in that specific, accurate context.
Mhm.
It bridges that gap.
And what's truly powerful about LlamaIndex is its versatility. While its primary focus is undeniably question answering with RAG,
That's its bread and butter.
right, but it's also fantastic for building sophisticated chatbots that can maintain multi-turn conversations and intelligently clarify questions.
Very useful for complex interactions.
And it excels at document understanding and data extraction, allowing LLMs to semantically identify and pull out precise details from, vast amounts of unstructured data.
Super helpful for analysis. So, to show you how it orchestrates those RBAG steps we just heard about, LlamaIndex handles it beautifully.
It really streamlines the process.
First, it manages loading and chunking your raw documents. Takes your big documents and intelligently breaks them down into smaller, manageable text chunks.
The chunking is key. We'll come back to that.
Definitely. Then, for embedding document chunks, each of these chunks is converted into its unique numerical vector, its semantic GPS coordinate.
Using an embedding model.
Right. These vectors are then stored in a specialized vector database. Now, when you provide a user prompt, that question is also embedded into a vector using the exact same embedding model as your documents.
Crucial point. The same model.
Absolutely crucial. We'll probably say that again.
Probably. Consistency is everything there.
Next, a LlamaIndex component performs the retrieval. It uses your prompt's embedding to find and pull out the most relevant chunks from that vector database.
Based on that similarity search we mentioned.
Exactly. This retrieved text is then used for prompt augmentation, where it's strategically added as context to your original user prompt.
Giving the LLM the needed background.
And finally, for LLM response generation, this now augmented prompt is sent to your chosen LLM, which, armed with all that fresh context, can provide a perfectly context-aware answer.
So LlamaIndex kind of manages that whole workflow.
Precisely. It's the conductor of the orchestra.
Nice. And one of LlamaIndex's clever solutions for simplifying this is how it handles your data. It organizes all your document sources using a generic document class.
A document class?
Yeah, think of it as a smart data container. It holds not just the actual text, but also a unique ID it's embedding if it's already generated, and really valuable metadata.
Metadata like?
Things like where the document came from, the file name, when it was created, maybe who authored it. This metadata is super key for more advanced retrieval later on.
Right, for filtering and stuff.
Exactly. And getting your data into LlamaIndex is also super flexible. You can load text from all sorts of local files, PDFs, Markdown, CSVs, even HTML.
Standard stuff.
Yeah, or you can connect directly to databases and cloud storage using its many built-in connectors.
Oh, nice.
And a particularly handy tool is the Simple Directory Reader.
Sample directory reader.
It can effortlessly pull in all files from a directory, including subdirectories or just specific file types you tell it to look for. It then spits out a list of those smart document objects ready to be processed.
That simple directory reader sounds incredibly useful. Just point it at a folder.
Pretty much, yeah. Makes ingestion much simpler.
But then we get to this idea of chunking documents, which you mentioned, and LlamaIndex calls nodes. What's the real insight here? Why is breaking things into these smaller nodes so critical beyond just making them, manageable?
That's a fantastic question because chunking isn't just about file size or fitting into a context window, although that's part of it. It's really about semantic coherence.
Semantic coherence,
Yeah.
meaning?
Meaning, the purpose of chunking is to ensure that each small segment of text retains enough specific context to be meaningful on its own. If a chunk is too big, the LLM's context window might get overwhelmed or the key info gets lost in the noise.
Right, the needle in the haystack problem.
Exactly. But if it's too small, you might lose vital surrounding context needed to understand that piece properly. It's truly where art meets science. You're aiming for chunks that are semantically complete.
Makes sense.
This leads to much more precise and relevant embeddings for retrieval later. Good chunks make good embeddings.
So how does LlamaIndex help with that chunking art?
Well, it offers tools like Sentence Splitter, which does a great job for many kinds of text. It intelligently tries to split long text based on natural breaks like sentences, paragraphs, new lines, or periods.
Okay.
And you have control over the chunk size. That's the maximum number of tokens, basically words or parts of words, per chunk and chunk overlap.
Chunk overlap?
Yeah, that determines how many tokens can overlap between consecutive chunks. This overlap is actually crucial for maintaining context across the boundaries where you split the text. So the end of one chunk repeats at the start of the next.
Ah, so you don't lose the connection between ideas?
Precisely. It helps preserve the flow. LlamaIndex outputs these as text node instances. And it offers other splitters too, even wrappers, for tools from other libraries like LangChain.
Okay, so LlamaIndex sounds like the orchestrator making all these pieces, loading, chunking, embedding, retrieving, generating, play together nicely.
That's a good way to think about it.
But all those embeddings, those semantic GPS coordinates, they need a home, right? A place where they can be quickly found and matched for similarity.
Absolutely. They need efficient storage and querying.
And that's the role of a vector database, and ChromaDB is a fantastic example, especially if you're building ARG applications locally, maybe just starting out.
It's become really popular for that, yeah.
So what exactly is ChromaDB? Can you break that down?
Sure. Imagine you have that massive library again, but instead of searching by keywords on index cards, you want to search by the actual meaning of the content.
Okay.
That's basically what ChromaDB lets you do. It's an open source vector database designed from the ground up specifically to store and manage those embeddings, those long lists of numbers representing meaning.
The GPS coordinates.
Exactly. And crucially, it's also designed to store their associated original text chunks and any useful metadata alongside them.
So it keeps the number and the original words together.
Right. And unlike traditional databases optimized for tables and keyword matching, a vector database like ChromaDB is optimized to store and quickly search these numerical embeddings based on their semantic similarity.
That similarity we talked about measured by distance or cosine similarity.
Precisely. It's like having a library where the books automatically rearrange themselves so that similar concepts are shelved together, even if they use different words.
That's a powerful idea. So how does ChromaDB fit into the RA puzzle then? How does it allow LLMs to look up facts?
Well, it essentially acts as the intelligent, searchable memory for your LLM's external knowledge.
The LLM's external brain.
Kind of, yeah. First, in data ingestion and embedding, you process your documents, split them into those smart chunks.
Using something like LlamaIndex.
Right. And an embedding model converts each text chunk into its numerical vector embedding. ChromaDB then stores these embeddings alongside the original text chunks and any crucial metadata like title, author, date, which, as you said, is incredibly useful for filtering later.
Okay, so load it all in.
Then, for user query and retrieval, when you ask a question, your question gets converted into an embedding using the same embedding model. Again, consistency.
There it is again, same model.
Always.
Okay.
This query embedding goes to ChromaDB, which performs a rapid similarity search. It uses clever algorithms, like HNSW, which we can touch on, to quickly find the top N most semantically similar embeddings.
Top N, so maybe the top 5 or 10 closest matches.
Exactly. You can usually specify how many you want. It then retrieves the original text chunks and their metadata associated with those top embeddings.
Got it.
Finally, for augmentation and generation, these retrieved relevant text chunks are then augmented, basically, added as context to your original user query. This augmented prompt is what gets sent to your LLM.
And the LLM, now seeing the question and the relevant facts from ChromaDB,
can generate a much more accurate, factual, and targeted answer, drastically reducing those infamous hallucinations or making things up.
It really seems to solve that core problem of LLMs not knowing specific current info.
It's a very elegant solution, really.
Yeah.
And ChromaDB has gained a lot of traction, especially for local RAIDs development, for a few compelling reasons.
Like what makes it stand out for, say, someone just starting with this?
Well, the biggest one, honestly, it's extreme ease of use and setup.
Yeah.
It really embraces a local-first philosophy.
Local first.
Meaning you can get it running with a simple pip install chromad. That's it.
Wow, okay.
And you can use it entirely in memory for quick tests, no file save, just running your computer's RAM, or easily persist your data to a local file on your hard drive.
So no complicated servers or cloud accounts needed to just try it out.
Exactly. This is a huge game changer for rapid prototyping and learning. You bypass complex Docker setups or signing up for cloud services just to get your feet wet. And its Python API is designed to be very intuitive.
That sounds really appealing for developers.
It really is. Another huge advantage is that it's built specifically for LLM applications. Unlike some general-purpose vector databases that added vector search later, ChromaDB was designed with RAG workflows in mind from the start.
How does that manifest?
Well, it handles the document storage, the embeddings, and the metadata, filtering in ways that directly support these common ARN patterns. It can even take care of the embedding generation step for you automatically if you want it to.
Oh, that's handy.
Yeah. And speaking of flexibility, it offers different storage options. There's the in-memory option, super fast for dev cycles, but remember, data is lost when your program stops.
Right, ephemeral.
And then there's persistent local disk storage, which saves your data to your hard drive. That's perfect for ongoing projects or larger data sets you want to keep around.
Makes sense. In memory for quick tests, persistent for real work.
Exactly. Its integrations are also excellent. It has native tight connections with popular LLM orchestration frameworks like LangChain and LlamaIndex.
The ones we've been talking about.
Right, which really simplifies your development process. You don't have to write as much glue code.
How does it compare to other options, just briefly? Like, I've heard of Face or Pinecone.
Good question. So Phase S, developed by Facebook AI, is incredibly fast for just the similarity search part, but it's more of a library than a full database. It lacks easy persistence, metadata filtering, and the database management features ChromaDB provides out of the box.
Okay, so FAS is more like a specialized engine.
Kind of, yeah. Then you have the bigger, often cloud-based, production-ready vector databases like Pinecone or Weaviate. They're incredibly powerful, scalable, and feature-rich. But they can be overkill and significantly more complex to set up and manage, especially when you're just starting or learning locally.
Gotcha. More setup, maybe more cost.
Potentially, yeah. ChromaDB really hits that sweet spot. It maybe sacrifices some extreme, massive scale features for unparalleled ease of use in local development without giving up the core RAG necessities.
That makes perfect sense. It sounds like a great starting point. So the magic of ChromaDB for speed, you mentioned HNSW. How does it actually find those similar vectors so quickly?
Yeah. The secret sauce behind ChromaDB speed, especially for finding approximate nearest neighbors very quickly, is HNSW. It stands for Hierarchical Navigable Small World.
Hierarchical Navigable Small World. Okay, what does that mean in plain English?
Yeah, it's a mouthful. Think of it like a super efficient, multi-layered road network built over your data points, your vectors. It lets you navigate quickly to the general vicinity of your target vector on higher, coarser layers, and then zoom in for more precision on lower, denser layers.
So it doesn't have to check every single point?
Exactly. It avoids checking most of the data points. It's designed for approximate nearest neighbor, ANN searches. This means it finds points that are very likely to be among the true nearest neighbors, extremely fast, even if it's not mathematically guaranteed to be the absolute closest every single time. For RBAG, this trade-off is usually perfect. Speed is often more critical than absolute mathematical perfection.
So it's fast and good enough for finding relevant documents.
Precisely. And you can even tune HNSW's parameters, things like how thoroughly it searches or how densely connected the graph is to balance speed, memory usage, and accuracy for your specific needs.
Interesting. And you mentioned filtering earlier, combining semantic search with metadata. How does ChromaDB handle that?
Right, this is where ChromaDB gets really powerful for practical RAG. It lets you refine your searches in two crucial ways, and you can even combine them.
Okay.
First, there's metadata filtering. This lets you filter based on that structured data you attach to your documents: source, version, author, date, whatever key value pairs you defined. You can use standard logical operators like equals, greater than, in a list, and, or to pinpoint exactly what you need.
So like find documents from source X published after date Y.
Exactly like that.
Yeah.
Second, there's document filtering. This is cool. It lets you filter based on actual keywords or phrases within the document text chunks themselves.
Oh, wow. So not just the metadata, but the content too.
Yep. You can say things like find vectors whose documents contain the word pandas. You use operators like to contains or not contains.
So you could do a semantic search for, say, data analysis techniques and then filter those results to only include documents that specifically mention pandas.
You absolutely can. You combine the semantic similarity search with both metadata, where clauses, and document content, where document clauses in the same query. This combined power makes ChromaDB incredibly effective for building precise RJAD applications.
Okay, that sounds incredibly powerful. So we've got the concepts, the frameworks like LlamaIndex, and the vector database like ChromaDB. Now for you, the listener, how do you actually roll up your sleeves and put this into practice? What does a RAG development workflow with ChromaDB really look like step by step?
Let's walk through a typical local workflow.
First, and simplest, you'd install ChromaDB. Like you said, usually just pip install chromab.
Yep, straightforward.
Second, you choose your storage mode. For quick experiments, maybe start with in-memory storage.
Wow.
Super fast, easy to reset, but remember, the data disappears when your program stops.
Right. Good for playing around.
For anything you want to keep, especially during development, use persistent local disk storage. Your data gets saved right there on your hard drive in a specified directory.
Definitely recommended for most development work.
Third, and this is where the real work begins, load and process your documents. You'd use document loaders, maybe from LlamaIndex, to read in your various file types.
Get the raw text in.
Then comes that crucial chunking process we discussed. We really can't stress this enough. LLMs have limited context windows. Smaller, semantically coherent chunks help the LLM find the most relevant information without getting overwhelmed.
It's worth spending time here.
Definitely. You'll want to experiment with chunk size, how big each piece should be, and chunk overlap, how much text overlaps between chunks to maintain that context across the breaks. Getting this right can seriously make or break your R-RAID system's accuracy.
Trial and error is often needed. Aim for chunks that make sense on their own.
Fourth, you'll create a ChromaDB collection and add data. A collection is just like a named table or storage area within ChromaDB. You create one, maybe give it a name like Project Docs, and then you feed it your process chunks.
And ChromaDB is smart enough, often, to handle the embedding step for you here if you haven't done it already.
Yeah.
You pass it the text, tell it which embedding model to use, or use its default, and it stores the text, metadata, and the generated embedding.
Super convenient. Fifth, perform retrieval, which is just the fancy term for querying ChromaDB. When a user asks a question,
You embed the question using the same model.
right, and then you query the ChromaDB collection, asking it for the top N most similar document chunks based on their vector similarity.
And maybe add some metadata or document filters too.
Exactly. And finally, sixth, integrate with your local LLM. This is the core RA part. This is where everything clicks together. You'll set up your local LLM, perhaps using a handy tool like Llama to run models easily. Then you connect ChromaDB to a framework like LlamaIndex or LangChain.
Using their ChromaDB integrations.
Yep. You create a retriever component within the framework that knows how to query your ChromaDB collection. You define a prompt template to tell the LLM exactly how to structure its thinking, like, use the following context to answer the question. Context, question, question.
Guiding the LLM is important.
Very. And then you run a query engine or a chain that ties it all together automatically. It takes the user's question, uses the retriever to get relevant info from ChromaDB, puts it into the prompt template, and sends the whole thing to the LLM to generate that final, accurate, context-aware answer.
And that's the basic argy loop in action using ChromaDB in a framework.
Seems manageable when you break it down like that.
It is. But as you start building, it's good to keep some best practices in mind, especially for local RAG development.
Okay, let's hear them. What should people watch out for?
First, start small and clean. Seriously. Don't try to boil the ocean on day one by throwing your entire messy multi-format data lake at it.
Right.
Begin with just a few well-formatted documents. Get the pipeline working, end-to-end loading, chunking, embedding, storing, retrieving, generating, before you tackle the complexity of large, messy data sets.
Crawl, walk, run.
Exactly.
Yeah.
Second, and we keep saying this because it's vital, iterate on chunking. This is arguably the single most critical tuning knob for RAD performance.
More important than the LLMs sometimes.
Honestly, yes. Bad retrieval due to bad chunking means the LLM gets garbage context, leading to garbage answers no matter how good the LLM is. Experiment relentlessly with your chunk size and chunk overlap. Look at your document structure. Are they short articles, long chapters, code snippets? Aim for that semantic coherence in each chunk.
Got it. Chunking is job one.
Third, choose your embedding model wisely and be absolutely rigorously consistent. For local use, open-source sentence transformers models from Hugging Face, like All-Middle-LM L6v2 or maybe the newer Nomic Embed Text, are excellent starting points. They balance performance and resource usage well.
Good recommendations.
But here's the golden rule, the one you cannot break. Always use the same embedding model for both indexing your documents initially and for embedding your queries later. Mismatching these models will completely break your retrieval. The vectors won't be comparable.
Okay, hammering that one home. Same model, always.
Fourth, leverage metadata. Don't just store the text chunks. Remember those extra details you can attach: source file, author, date, page number, chapter, whatever makes sense for your data. Use them.
How?
This metadata allows for incredibly powerful filtering during retrieval using ChromaDB's where clause. Imagine asking, find documents about HR policies specifically from the 2024 handbook, and your RG system nails it because you attach the year and source as metadata. It makes retrieval much more precise.
That's a huge advantage over just semantic search.
It really is. Fifth, evaluate retrieval, not just the final LLM answer. This is a common mistake. Don't just look at the final text the LLM spits out and decide if it's good.
What should you look at then?
Dig deeper. Inspect the actual source documents that were retrieved by ChromaDB before they went to the LLM. Were they truly relevant to the question? Did the top result actually contain the answer? If not, the problem isn't necessarily the LLM, it's likely your retrieval step. That's your cue to adjust your chunking strategy. Maybe try a different embedding model, or refine how you phrase your queries.
Look under the hood at the retrieved context.
Exactly. And finally, prompt engineering for RAG is a specific skill. Craft your prompt template carefully. Clearly instruct the LLM to use the provided context. Tell it what to do if the context doesn't contain the answer ideally. Instruct it to say it doesn't know based on the provided information, rather than making something up or falling back on its general knowledge.
Control the hallucination tendency.
Precisely. And maybe a quick note on resource management. For very large local datasets, keep an eye on your RAM usage, especially if you're using ChromaDB's in-memory mode. Persistent storage is generally more forgiving on memory.
Good practical tip.
And one final important insight, maybe. While vector databases like ChromaDB are brilliant for the core storage and fast retrieval, many essential RAG tasks typically happen outside the database itself.
Oh, like what?
Well, the initial document chunking usually happens before data hits ChromaDB. Any advanced retrieval logic, like maybe re-ranking the results from ChromaDB based on some other criteria, often happens after retrieval. The final prompt augmentation, or the actual process of combining the retrieved text snippets with the user's original question into the final prompt for the LLM, happens next. And of course, the direct LLM integration and response generation.
So the vector database is a critical component, but not the whole story.
Exactly. It's the specialized library, but you still need the librarian and the person asking the question and the writer synthesizing the answer. This is precisely why RAG frameworks like LlamaIndex and LangChain are so incredibly valuable.
Because they manage that whole pipeline.
Yes. They wrap around your vector database like ChromaDB and orchestrate that entire complex pipeline from preparing your documents through chunking, embedding, storing, retrieving, augmenting the prompt, interacting with the LLM, and finally giving you the answer.
Yeah.
They simplify the development process immensely.
Wow. Okay. We've really taken a fascinating deep dive today into retrieval-augmented generation, that secret sauce that transforms LLMs from these brilliant, but sometimes, flaky generalists.
Confidently wrong.
It was highly accurate, context-aware experts grounded in specific data. We've seen how RAG works, its essential steps: embedding, retrieval, augmentation, generation, and how LlamaIndex acts as an incredible framework to orchestrate this entire, often complex process.
Absolutely. And we've really highlighted the pivotal role of vector databases, specifically ChromaDB, as that intelligent filing cabinet, that external memory for all that critical external knowledge.
Right.
It truly is the backbone that solves those core LLM challenges we opened with, the limited context windows, the outdated knowledge, and those dreaded hallucinations.
And those pitfalls to avoid seem critical.
They really are. Just to recap the big ones.
Yeah.
Never use different embedding models for indexing and querying. Pay close, careful attention to your chunking strategy. It's often make or break. And always test and tune your results by inspecting what's actually being retrieved, not just the final LLM output.
Solid advice. So, what does this all mean for you listening right now? RAG, LlamaIndex, and ChromaDB aren't just technical jargon to impress your colleagues, are they?
Not at all. They are practical, powerful tools.
They empower you to build AI systems truly grounded in your unique data. Imagine an LLM that understands every nuance of your personal meeting notes, or a chatbot that provides perfectly accurate, up-to-date answers about your specific company policies every single time.
That's the potential here, moving beyond generic AI.
Exactly. This technology allows you to move beyond generic AI to truly specialized, factual intelligence tailored to your specific needs and knowledge bases. So, the final thought for you is, what kind of custom knowledge-driven AI will you build next now that you know how to give it a perfect, precise memory?